to this year's Mindlin Lecture in mechanics. This is the most important lecture that the Department of Civil Engineering and Engineering Mechanics has. Mindlin is a giant in mechanics. He was a professor here in our department for a very long time, and he is known for major contributions in theory of elasticity and continuum mechanics. Unfortunately, this year we don't have Professor DiMaggio here, who has a lot of details about Professor Mindlin's life. But what I want to say is that Professor Mindlin, on top of his major contributions in mechanics, he was responsible also of creating an amazing group in mechanics in this department in the 1940s, 50s, and 60s. This group at the time was one of the top mechanics groups in the world, and Professor Mindlin was clearly the leader of that group. Now, among the many recognitions of Professor Mindlin, I would like to mention one that is not very well known. He received the Presidential Medal of Excellence in Science for his contributions during World War II in developing the proximity radar. And among the other numerous major awards that he has received, I would like to mention the Theodore von Karman Medal from the Engineering Mechanics Institute of the American Society of Civil Engineers, and he was also a member of the National Academy of Engineering. Today, we have the honor and the privilege of having someone who has received the Theodore von Karman Medal and is also a member of the National Academy of Engineering, exactly like Professor Mindlin. Professor Gao from Brown University, and I would like to invite Professor Ho Ling to provide a more detailed biographical sketch of Professor Gao.
I think you have seen the bio here in the announcement, so I make only a very brief introduction about Professor Gao. I met him actually in one of the engineering mechanics conference. It was probably around 20 years ago. So that was we first met. About Professor Gao, he received his bachelor's from Xi'an University. They produced a lot of very talented engineering mechanics students. And then he came to the US to have his master's and PhD from Harvard University. And after that, he moved on to become the professor at Stanford, and then also until full professor at Stanford, of course, and then he became director at Max Planck Institute in Germany for 5 years, and after that he returned to US, and now is a professor at Brown University, actually since 2006. So Professor Gao is working on many fields with the basic principles that control mechanical properties and behavior of materials in both engineering and biological systems. So as Professor George said, that he's a member of National Academy of Engineering, and then also the member of German National Science Academy and the Chinese Academy of Sciences. And he has received various awards and medals. So Professor Theodore is mentioned about von Karman, and others like John Simon Guggenheim Fellowship and Ronnie Hill Prize in Solid Mechanics for IUTAN, and Praga Medal from the Society of Engineering Sciences, and another medal from ASME, etc. So without delaying further, let me invite Professor Gao to deliver his Mindlin lecture for PC. Professor Gao.
Okay, thank you, George. Thank you, Ho, for your invitation and nice introduction. This is I've been to Columbia a couple of times. Each time within a different department. I think it is my first time to visit civil engineering. It's my great honor and pleasure. I am connected to, I'm thinking of my connection to Mindlin. I can identify two. One is 30 years ago, I was hired at Stanford University. The person who hired me, George Herman, was a postdoc of Mindlin. Okay, that's the first connection. So I worked very closely with George for a couple of years before he retired from Stanford. Second connection is Mindlin's first student. This is actually Paul mentioned to me. Mindlin's first student, Dan Drucker, actually was a very famous professor at Brown University. He was at Brown for 20 years, faculty member. In fact, Dan Drucker was a postdoc advisor to my own PhD advisor, Jim Rice. So I feel like I'm connecting to Mindlin in multiple ways. Okay, so today I'm going to be talking about some work I did in the last 10 years or so. It's kind of interdisciplinary. So my interest spans over engineering and biological systems. So I'll be talking about interdisciplinary topic, interface between material science and biology, essentially. Okay, so how cells interact with nanomaterials. Okay, the background of that is two areas I can identify. Although I'm working on the kind of fundamental side. Okay, the application for this kind of topics. First one is nanomedicine. Okay. People talk about using engineering nanomedicine. Okay, so I'll give you an example of how using cell nanomaterial direct understanding that help us develop nanomedicine. Second one is nanotoxicology. Right? So we're making a lot of nanomaterials, but we don't know their effect on health and environment. So let me first acknowledge a couple of co-workers. So Wen Hong Su, there is there a So I'll continue here. So Wen Hong is a postdoc. Okay, postdoc was near Brown. And so he's the lead person in my group who's working in this area. Shane is a former PhD student. He's now faculty member at Peking University. And Gui is a younger, more junior PhD student. Okay. I've had a lot of collaborations, and mainly this is faculty collaborator. This is not possible to see everybody here. Bob Kirk from Brown Engineering Brown. Agnes King from Brown Medical School, and Mel Nakis, Prohovska, and Michael Gilmore from Brown and Northwestern Harvard. All right, so some background. So mechanics of cell nanomaterial interactions. We've written a couple of review papers in the last couple of years. The problems involve, basically there are several fundamental questions we'd like to understand. First one is the cell uptake pathways. So how do the nanomaterial get into cells? Okay, by which mode, what kind of interaction? Okay. These are, in particular, the nanomaterial can have different geometrical parameters. There are shape, size, orientation. There are mechanical properties, maybe stiffness of the particle play a role, and then chemical properties like surface oxidation. All these different properties can influence how cell uptake of nanomaterials. And also, once the nanomaterials get into cells, how do they package? Okay, so what are destiny within cells? How do they induce, for example, toxicity and so forth? So I have some picture there. You can imagine these materials of different sizes. They can be spheres, they can be 2D materials, they can be soft and stiff, they can be long and short, right? So how these materials? So there's a schematic of current understanding. Okay. So this is the same as virus. Virus give the cells. Virus are all nanoparticles. So viruses induce so-called ligand receptor binding. Okay. So cell surface of receptors. Receptor can bind with the surface of nanoparticles, induce cell membrane to bend, okay, to bend over a nanoparticle and take that in. This is a mechanical process. Okay, so in this process, we like to study. All right. So let me give you some background. All right. So first one, let me give you the background of nanotoxicology. Because a lot of people are interested in what are the biological and environmental impact of nanomaterials. Right? For example, the engineered nanomaterial, these are not evolved, not a result of natural evolution. These are man-made materials. But over the last 2 decades, the man-made engineered nanomaterial become a substantial fraction of global material flow. Okay, it's estimated, this estimate was like almost 10 years ago. Okay. But the number is roughly similar even today. There's about 300,000 tons of engineered nanomaterial each year. All right. And large fraction of them, 60 to 90% of them, end up in landfill. They end up just waste, right? Product end up in the environment. So we don't know how they affected the ecosystem and environment biology. So it's important to understand where do they go, how their long-term effect on health. 2 examples of carbon nanotube. Right? These are more recent nanomaterials. Carbon nanotube production right now, 5 years ago, was several thousand tons per year. Okay, there's a lot of increasing applications like energy storage, automotive parts, boat, sporting goods, lots of applications. Right? Graphene is the newest nanomaterials. In 2009, it's like the annual production is 15 tons. By 2014, it became 150 tons. So exponential growth of these materials. So the background is important to understand how they influence biological systems. Okay. Now, nanomedicine, a lot of my colleagues talk about cancer. Cancer is the main target of nanomedicine, application of nanomaterial to target cancer. Right? So I'm not going to speak about cancer today. I'm going to speak about antibiotics. Okay. This is why we can select a lot of examples to talk about. Okay, so let me tell you a little bit about antibiotics, how nanoparticles will help us develop new medicine for antibiotics. Okay, because it's known that the huge benefit of modern medicine is antibiotic. Okay, without antibiotic, large fraction of human population will not exist. Okay, the history is not that long, maybe 100 years. Right? So on this line is the drug development, new antibiotic being developed. Okay. And let's call them antibody resistance. So whenever we had a new drug, very quickly, over a couple of years, the bacteria develop resistance. Okay, they become insensitive to drug anymore. So that's why you have like a war. Okay? You have to develop new drugs, and yet the bacteria develop resistance. You have to compete. Okay, but clearly now we're losing that war. For the last decade or so, there's no new antibody emerged. The drug development has been slowed down a lot. It's very hard to discover new drugs, new antibiotics. Right? So now what's the challenge? Okay, now in the hospital there's something called superbugs. Superbugs are bacteria that resist all known antibiotics. None of the drug work. Okay, so it's called looming crisis. The World Health Organization have issued a crisis warning for the last couple of years. Right. So the challenge is the new antibiotic, right? The traditionally antibiotic, the most existing antibiotic, they all designed to target protein, cell wall, gene synthesis. Okay, they're developed to target some business pathways. And bacteria is always able to develop new pathways to synthesize some molecules after a couple of years. Okay. So it's like you block one pathway, the nature will find another. Right? So that's how bacteria develop this resistance. Okay. And more seriously, when the drug was put into action, some bacteria just go to sleep. Okay, they stop multiplying, they stop synthesizing. So you cannot deal with such bacteria. It's called persisters. That's a big problem, right? When the bacteria go to sleep, no antibiotic will work. Okay, so the persisters are hard to kill. And yet, when you stop, when the drug is stopped, they can wake up, right? So they're still surviving. Okay, so the potential solution, one of the potential solutions, first of all, because innovation has slowed down, we wanted to accelerate innovation. Can we use modeling simulation to speed up the pace of drug and new drug discovery? Right? That's one idea. We use mechanics, using modeling simulation to help people speed up the time, to shorten the time to discover new drugs. One particular example I'm talking today is we're going to design some membrane-active antibody. Okay, because instead of targeting a synthesis pathway, the traditional approach, okay, membrane is a universal structure in bacteria. Okay. Even the sleeping bacteria, the persisters, they still have a membrane. So we can design some nanomolecules or nanomaterials to destroy the bacterial membrane, but not a human membrane. Okay, you have to be very selective. That's why design is very important. Then we can design membrane-active antibody that kill persisters. That's the challenge. All right. Okay. So this research topic would have been very difficult even 10 years ago, because we didn't have good imaging techniques. But today, a lot of things have changed. During the last 20 years, there's huge development in bioimaging techniques. Okay. So-called optical microscopy and nanoscale. 2014 Nobel Prize in Chemistry was awarded to 3 scientists who developed the super result fluorescence microscopy. Right? So the citation of them is to bring optical microscopy to nano dimension. Because in biology, the main tool is optical microscopy. Because you use electron microscopy, then you have to study dead material. You have to kill the cell first. So that's a major disadvantage. So optical microscopy is the primary tool to study dynamic biological processes, but yet the optical microscopy is limited by the wavelengths of the light. Right? That's well known. You cannot see clearly what's going on within the cell. Right? So using fluorescence molecule interfering in the fluorescence, and so we have a lot of advance in the last 20 years. Okay, so let me see here. These are 2 pictures are the. So this picture on the upper right are the electron microscopy for dead cell, right? So now the last two pictures are the optical microscopy. We can see that the picture shows we can now use an optical microscopy to see exactly the same structure as in electron microscopy. Furthermore, more importantly, we can study dynamics. Okay. This structure is called fibrator structure on the cell surface. Okay, the pseudo legs. These structures play very important in cell motility, cell migration, and things. Right. So their structure, their thickness is about, their diameter is about a few tens of nanometers. Would it be possible to study using traditional optical microscopy? But now you can see their evolution of this. So this kind of imaging techniques play a very important role in helping us try to cognitively model the systems. So today I know I don't have too much time. It's a highly interdisciplinary topic. So I'm just going to select 3 topics, okay, 3 examples of demonstrating the use of mechanics as a tool to understand the cell nanomaterial interaction. First one, 3 examples by cell. First example, something with morphology. Okay. Understanding cell entry of a 1D nanomaterial, how a fiber enters cells. Use the mechanics of the tool to understand. Second is the packaging problem. This has to do with the cytotoxicity of a flexible CNT nanofibers. The third one is energy mapping. Particularly, we're trying to design this membrane-active antibiotics. So I'm just giving you 3 examples to demonstrate this area, this research area. Okay. So first example, I want you to imagine I have a carbon nanotube or some nanofiber in the process of entering cell, as that picture shows. Okay? So I can write down the free energy of the system, mechanics, right? We always deal with the energy. So this is the free energy of the system, right? So 2 terms. The first term is the membrane bending energy, because for that nanomaterial to go into cell, the membrane has to wrap around the particle, okay, form a curved surface. That causes bending energy, right? Bending elastic energy. So kappa is the bending rigidity. H is the mean Gaussian curvature of the surface, the cell surface, the integral of the area. The second term, sigma delta A, is the membrane tension energy. Okay. The membrane tension energy, the membrane tension also physical parameters as known. delta A is the change in membrane surface due to the insertion of the nanomaterial. So these two energies compete with each other to govern the uptake process. So this whole physical process, from that free energy, there's only one non-dimensional parameter. We do a dimensional analysis. Only one dimensional parameter, which is a sigma bar, right? 2 sigma, the membrane tension, scaled by square the diameter, radius of the fiber, divided by bending rigidity, right? This is a non-dimensional parameter, right? So exists a critical number, this non-dimensional parameter. When the critical number is given by 2 pi over 5, sigma c, if this non-dimensional number is smaller than this critical value, right? So the fiber will go into cell in a perpendicular way, normal to the cell surface. Right? If that non-dimensional number is bigger than this critical value, 2 pi over 5, then the fiber will go parallel to the membrane surface. Okay? And this sigma c, right, the critical non-dimensional number can also be interpreted as a critical size for nanomaterial. Right? So sigma equal to sigma c can be interpreted as A equal to AC, the size. The size of the fiber is about 5 sigma pi kappa. It's about 40 to 100 nanometers. So it's about 100 nanometers, nanoscale dimension. Right? Okay. So here I show you the free energy change. When sigma equal to 1, that is the subcritical case, right? It's smaller than 2 pi over 5. In this case, the red curve is the bending energy variation as a function of entry angle, the inclination angle theta. Right? You can see the bending energy decreases with the angle of entry and minimizes at 90 degree perpendicular. The blue curve is the tension energy. Tension energy increases with the angle of entry. Right? So this is the total energy. The black curve is the total free energy. So in this case, the free energy is minimized with a physical 90 degree, when the fiber is already normal to the cell surface. So in the supercritical case, when sigma equal to 3 is bigger than 2 pi over 5, the bending energy still favors 90 degree, but in this case, the tension energy becomes dominant. So total free energy is this, right? It's minimized at a very small angle. So this could be understood by some simple analytical formula, right? Imagine in a subcritical case, let's consider extreme case, when this non-dimensional equal to 0, when sigma y equal to 0, that means that there's no membrane tension. Bending energy dominates. In this case, we only have bending energy. Since the energy is positive, in this case, the minimum energy surface corresponds to a mathematical surface called catenoid. Because catenoid is what I draw here. Catenoid is described by these mathematical functions. Okay. Catenoid is a very well-known and very important mathematical surface in 3D. Okay. It has a very interesting property. It's a curved surface, yet its mean Gaussian curvature is exactly 0 every point on the surface. Okay. Because the Gaussian curvature is plus minus, right? So the mean is 0, the edge is 0. So the catenoid, if the cell surface adopts in the configuration of a catenoid, it causes no bending energy. This is surprising, right, to engineer, because the engineer in typical plates or shells, any bending would cause energy. But a cell membrane, because it's a fluid membrane, actually there is a particular geometric shape, catenoid. The bending energy is exactly 0. Okay, so this is why when the bending energy dominates, the nanomaterial wants to go into cell, normal to the cell surface, because the catenoid is a minimum energy configuration, minimum energy state. In the supercritical case, when sigma bar is bigger than that, tension energy dominates. So in this case, imagine you ignore the bending term. You only consider the tension term, right? So tension energy is sigma delta A, right? Delta is a change in membrane area due to insertion of nanomaterial. So delta A is AC minus pi a squared over sine theta, right? In this case, you ignore the bending. So you can see that when theta equals 0, that one's minimized. Right? So both cases are pretty easy to understand. Okay, so now we're going to verify using experiments. So theory predicts there's a critical fiber size, right? When the fiber size is smaller than this AC, right, 5 sigma over pi kappa, then we have the perpendicular entry mode. So we can test, we can feed the cells, okay, with various nanomaterials, including carbon nanotube. So we've done lots of experiments with nanotubes, with gold nanowires, with asbestos fibers. We feed them with different materials. In the bending dominant regime, okay, within subcritical regime, we find each case, okay, this material going to cell in a perpendicular way. Okay, we're like a tree kind of around. This is like a bullet shooting some armor, right? But yet there's no dynamics. This is a spontaneous process, a spontaneous biophysical process. The bending deformation of the membrane automatically orient the fiber into 90-degree orientation. Okay. And when we have fiber bundles, okay, when we have bundles of these fibers, in fact, really is large, right? When you these fiber bundled together, we have an effective large radius. Then we find experiments. We have bundles. Those bundles tend to lie parallel to the cell surface. So agree with our theory. But ideal experiments, okay, an ideal experiment would be if you can feed the cell with a fiber, but the fiber really is growing. It's like a cell interaction with a growing fiber. That would be an ideal experiment. Our theory would predict initially the fiber would go normal to the cell surface, but once it grows to a critical size, right, it will lie down. That's an ideal experiment. But actually nature does the experiment for us. Okay. The Philopodia dynamics, living cells. This is the movie I showed you in the beginning. Philopodia is a very important structure on the cell surface. It's not a nanomaterial, okay, but mathematical formula is exactly the same. If you write on free energy system, it's exactly the same as the fiber entering cell. Okay. Philopodia is a growing fiber. Okay. Philopodia is a microtubulus. It's a protein stick out within the cell membrane, poke out the cell membrane. Okay. And when these microtubula merge together, okay, so in the upper figure, the experiment showed that the growth dynamics of Philopodia, you can see initially there are separate microtubula protruding out of the cell membrane. When they merge, okay, Philopodia growing diameter, okay, they grow. So this is like an ideal experiment for us, okay, even though it's not a design experiment. It's what's happening in nature, okay, when the Philopodia is formed. Right? So again, our theory, we write down free energy, our theory would predict at a critical diameter when the Philopodia grow to critical diameter about 40, depending on cell type, right? And varies. Then the Philopodia should first stand up, then lie down, right? So when we look at this movie again, okay, this movie was only able to be made by this new bioimaging technique only a couple years ago. That we can see that this Philopodia, right? They all undergo some mechanical instability. Right? They lie down. So initially they stand up in the cell membrane, and at a critical diameter they lie down. We can also, of course, verify this theory using simulations. Okay, like this kind of simulation. We can use molecular dynamics to simulate, right? To demonstrate this is a physical process. This is not no motors or biological metabolism needed, right? So we can have a cell membrane. We can orient initially a fiber arbitrary angle and show the deformation of the membrane was spontaneously oriented. Okay, angle spontaneously oriented toward 90 degrees. Okay. So fully agreeing with our experiments. But so we can also tune the diameter, right? If the non-dimensional membrane tension we selected to be 0.3, the subcritical case, we see the orient like this. We select a big number, supercritical 7.4, then the nanomaterial will lie down, right? In full agreement with this. Okay, so what is the significance of the two biological system, right? So far we understand there's an interaction modes, perpendicular entry and parallel entry. So what's the significance to biology or to medicine? Right? So we take example of the so-called asbestos nanofiber. Asbestos fibers was used profusely about last century for building household, for insulation. Lots of companies in 1930s, 1940s, but now they all went bankrupt. What is the asbestos company? You know why? Because of lawsuit. Over the years, people discovered asbestos fibers cause lung cancer. Okay, they cause lung cancer, but yet this is only empirical. That's why there's a lot of lawsuit. And there's no mechanistic understanding of what's going on, right? But now we have a theory. We can begin to look at the system, right? What happens if the cell sees asbestos fibers? Because asbestos nanofiber is very thin, right? So the cell will tend to grab the fiber tip because this is perpendicular entry mode, right? Cell sees nanofiber, grab the fiber tip, and then fiber gets into the cell. What if the fiber is very long? Okay, like in this case, this is a nanotube, but it can be asbestos fiber too. If the fiber is very long, then the cell really get confused. Okay, because of these cells, their task is to ingest this nanomaterial, and then remove them from a human body. Okay, but asbestos fibers or common nanotube, there's a lot of fibers. They're not short fibers. They're much more for cell to deal with. Okay, so cell, you can see this picture here, right? So cell become like stuck on these fibers, and the fiber cannot be easily degraded. So this is called frustrated endocytosis or frustrated phagocytosis. So this, when this happens, the cell, imagine this is like a police stop a criminal, but the criminal is too powerful, right? So what happens is this cell will call for help. Okay, the cell will send a lot of signals and cause local inflammations for many years, right? For many cells, for many immune cells come grouped together, form a tumor eventually. Okay, so this is origin. So actually, not surprisingly, when people study cell interaction with carbon nanotube, they see exactly asbestos-like disease, right? They say mesothelioma, lining of mice to carbon results in asbestos-like lens-dependent pathogenic behavior. So this asbestos problem, this cancer problem is actually the original cause, not chemistry. It's not because of the chemical composition of the material. It's a mechanical problem. Okay? It's just the geometry problem, actually, the origin of this. Now, my second example has the packaging problem. Okay? Packaging. Now, imagine when the nanomaterial gets into the cell. Okay? The nanomaterial has been ingested, has been taken into the cell. What happens? So once the nanomaterial gets into the cell, it will be sent to the packaging lysosome. Okay? Lysosome is a packet of lots of enzymes, lots of degrading enzymes. Lysosome is responsible for digestion, for degrading bacteria, degrading foreign materials. Okay, so it's very powerful compartments. Okay, so you have the packaging problem. Okay, so we ask a question, right? So when the biology interacts with materials, right? People think some material is stiff, some material are hard. Right? So what is a bio-stiff? What is bio-soft? So we study this problem. We find the definition of bio-stiff and bio-stiff, bio-soft can be for fiber can be defined the following way. Okay, if I have a fiber long fiber packaged in lysosome, okay, because it's trying to protrude in there, so there's two pinch force, two compressive force at the end. If the fiber buckles, right, the buckles and coil within the lysosome, then we define that material as bio-soft, okay, because it doesn't fight against the nature, because the lysosome is trying to package this problem with this material. If this material is too stiff, okay, if it is soft enough, it will coil around, it will give yield, will yield the biological confinement. On the other hand, okay, if the material are stiff enough, they can resist buckling. Okay, you have the following scenario. This fiber will sticking out, will be very stubbornly persisting in the material in the lysosome, sticking out its head in this way, right? That's a bio-stiff material. Okay. So So we look at this problem, we find biostiff is the origin of toxicity. Okay, that's my story. Okay, because in the biostiff, if the material is stiff, you have a pinch for you. This environment here, okay, this environment here is a confining force. Okay, confining force. This is like remind us of a nano indentation. Okay, indentation, except it's indenting a membrane, not indenting the material. Okay, so this is like a nanofiber indenting on a piece of membrane. Okay. If there's an indenting force, that could cause lots of problems, mechanical damage locally, as shown below. Okay. Because these fibers are hydrophobic, right? These are atomic material, nanomaterial. These are atomically perfect material with a close contact. They can cause the membrane lipid extraction. They can cause lipid to be extracted from the membrane. Okay, with the indenting force. Right. So in the material science, you can call it a creep indentation. Right? We would put an indenting there, and the membrane would yield and some flow, something, right? Plastic flow around the indenting. And because of the membrane, the lipid is extracted from the membrane, that can cause the leakage. Okay, cause the lysosome to leak. Okay. So persistent contact leads to membrane damage due to lipid extraction. So we've tested, my collaborator, we have tested tested this concept. So we culture cells with many different types of material. They all have the same chemistry. We decided to consider exactly the same chemistry, okay, just to avoid controversy. So we tested carbon nanotube, carbon black, okay, 1 micrometer long, stiff nanotube, half a micron long, stiff multiple nanotube, carbon black, just like powder, okay. Long and soft carbon nanotube is very long, but like single wall tubes, right? They're very soft. Okay. Tangle soft and carbon nanohorns. Nanohorns, they have sharp edges, but yet their dimension is small. Right? So what we found in that case, in the upper left case, that 1 micrometer long stiff carbon nanotube, all these have the same chemistry, right? Only in that case show toxicity. Okay. So here we measure the cathepsin B. Cathepsin B is an important enzyme within a protein within the lysosome. Release of cathepsin B is known to lead to cell death, apoptosis. Right? So we measured different cathepsin B release of cells with many different kinds of materials. We find only the stiff multiple carbon nanotube, 1 micrometer, there's a dosage-dependent release of cathepsin B. The more nanomaterial you feed, the more release of cathepsin B you have. Okay. And that, that shows this material does cause membrane damage. Okay. Because the protein that's supposed to be, the enzyme is supposed to be enclosed with the lysosome, not being leaked out. Okay, leaked out to the cytoplasm. And we can correlate cathepsin B release to cell death. Right? So we culture this cell with different nanomaterial for 24 hours. Then we measure the viability, means how many cells are surviving after 24 hours. Okay. So this dosage, right? So for example, carbon black, right? Carbon black, this line has no dosage dependent. Almost all cells survive. Okay. But this 1 micrometer long multiple carbon nanotube cell can die. Okay, more and more cell die. This is even longer nanotube. So these long and stiff carbon nanotubes, they induce cell death. So this experiment showed, right? Just like in our theory, shows the packaging issues. Okay, so based on this, this is like a confined buckling problem, right? Very well-known mechanics problem, confined buckling problem. So we developed a cytotoxicity phase diagram based on this concept. Okay, so on the vertical axis is the length of the nanofiber. Horizontal axis is the diameter of the nanofiber. Okay, nanofiber. So these are experimental data. The blues means they're biocompatible. Okay, they're not causing cell deaths. The red color data means cell deaths are observed. Okay, so what's happening in different corners? Okay, so we have this red regions. So this is the Euler buckling. This curve is Euler buckling curve. The buckling criteria of the fibers. Okay, so what happens here in that corner? Okay, in that upper left corner, the fibers are long and flexible. They're biosoft. Okay, so even if they can be well packaged with lysosome. So because the pinch force through the membrane can cause them to buckle and yield. Okay, they become nicely packaged. As we show you experiments there and simulation, right? So that corner is biocompatible. Okay, so in the red region, that's where we have this stiff material stick out of the lysosome. It causes lysosome permeability, cause leakage, right? That's where called lipid extraction cause damage, right? What happened in this region? Okay, what happened in this region is also biocompatible. That region is for short nanomaterial. When the fibers are short, right? When the fibers are short, because of thermal fluctuation, the short nanofiber, they can just fluctuate, move around within the lysosome without persistent contact. Okay, their contact point always change. They don't have any confinement issue there, so they're also compatible. So we identified in this phase diagram there's two regions for compatibility. One is short material, right? They're not causing any confinement issue, so they're compatible. And there's a biologically soft region that they can buckle and yield. They don't cause toxicity. It's the stiff and long fibers that cause toxicity. Okay. The third class of problems, my third example today, I'm talking about energy mapping. In this case, we're developing membrane-active antibiotic. So this is published today. We just have a Nature paper come out a week ago. So I'm just giving you 3 molecules here. Okay, so we test a lot of molecules working with medical people. So 3 molecules shown here, right? They're all like a 2-dimensional, 2D type of nanomaterial, 2D nanosheets type of material. All right, with similar, the first two with very similar chemical structures. One is oxygen, one is OH. The root is slightly different, right? But yet their effect on biological membrane is very different. Okay, so here we test. This is not cell. This is vesicle. Okay, we put this nanomaterial, culture this material together with the vesicle. Okay, there's no cytoskeeleton, anything, just a membrane. Okay. We see in the first case, that material has almost no effect on membrane. The membrane stayed pretty intact, no damage. Okay. The third case, this molecule caused membrane to rupture, cell membrane to rupture. The second one caused membrane to leak, form aggregations, part of leakage. Okay. So the cell membrane are quite sensitive to the biological material, okay, to their polar groups, to their geometry and everything. Okay. So we developed a method to calculate the energy profile for the interaction with nanomaterials with cell membrane. Right? This is called steered molecular dynamics in the biophysical community. Right? Specifically, the method called umbrella sampling. Okay, we can compute the free energy as a function of the distance between the nanomaterial and cell membrane. So as you bring this nanomaterial in the cell membrane, how the free energy changes. The free energy consists of interaction energy and entropy. Okay, both parts. So we see here, we calculate these 3 molecules. Okay, this molecule, which has no damage to the cell membrane. As we bring this molecule to the cell membrane, we see an energy barrier, right? Energy barrier. And then within the cell, this is within the cell membrane. We see a large energy barrier, and also the energy, even when the material goes into the cell membrane, is still higher than outside. Okay. So there's an upslope of energy. So in this case, the molecule does not do any damage to the cell membrane. The second case called aggregation, right? This causes membrane to leak. In this case, when we bring this to the cell membrane, we see a quite small energy barrier, But then there's a sink, right? It's favorable to bring this material within the cell membrane, okay, within the membrane. The third one is what's called membrane rupture. Okay, in this case, we have almost no energy barrier. This is energy drop, and there's a big energy drop when the material goes in the cell. Okay, so let me show again this experiment. Okay, this membrane. So at the podium, also that's a movie too. So this is a simulation of how this molecule interacts with the cell membrane. So that's energy profile we calculated. Okay. In the case of the adipolyme, that we don't see the molecule just doesn't penetrate into the cell membrane, into the membrane. And so experiment shows the membrane stays intact, there's no damage. In the second case, the CD437, was able to penetrate into and cause the cell lipid aggregation. In the third case, because there's large free energy gain, they cause to rupture, vesicle rupture. Okay, so we were very excited when we see these results. So our medical school collaborator even more excited. So they want to test this, right? They want to test this. So they test the CD437 and these two drugs for possible potential membrane antibiotic, membrane active antibiotic. Okay. The key is they shouldn't have any bacterial antibiotic resistance, okay, because this only target the membrane, no synthesis pathway. Right? So 437, it shows first of all fast killing persisters. Okay, persisters usually don't react to antibiotic, but they kill them very fast. Second, they have very low human toxicity. Okay, so right now we understand that human cells have cholesterol. Their structure is a little bit different from bacteria cell membrane. So because of cholesterols, okay, human membranes are, the energy map is a little bit different. Okay, the energy profile is very different. Okay, so most important is the low resistance probability. Okay, you can show this resistance. That curve, this growing curve, is we're measuring the dosage, the critical dosage for inhibition as a function of the time you feed the antibiotic. This is on mice. So the Cipro is an antibiotic drug in the market. Okay, you can see that within 2 weeks, bacterial resistance has been developed, and you have increase in resistance. Okay, about 80 days, and basically you need a huge dosage to kill the bacteria. Bacteria have developed a strong resistance, but yet the CD437, there's almost no resistance, even with 100 days. So this confirms our expectation for the membrane targeting. If we target the market membrane instead of synthesis pathway, the bacteria is not easily able to develop resistance. Okay. So anyway, so we're now pretty excited. We wanted to propose I'm writing an NSO proposal. So we want to see this simulation-based platform of using drug discovery optimization. We want to work with chemists and biologists and actual biomedical people. Okay, so in chemists, we're doing high throughput drug screening with combinatorial chemistry. Right? This is the usual drug development routine. But we want to use mechanics modeling simulation to help them. Okay, to help them understand the whole process, to map out the energy profile, to screen out human resistance versus bacterial resistance, that can help us speed up the pace for drug innovation. Okay. So modeling simulation, we are hoping that can facilitate screening, assessment, design, and optimization of synthetic antibiotic. Okay. So that's my last slides. So I'm just giving you some example today of how mechanics today can be used as a tool to help addressing some of the issues. Okay. So because there's a rapid advance in experimental and computational tools, okay, as well as unprecedented imaging capabilities. Right? So this combination, we have experimental tool, we have computational tool, we have an imaging tool. And these tools are making biology qualitative today, basically. Okay. It's no longer qualitative, we can qualitative study the system. Okay, I give 3 examples. First example I gave is study on the morphology of cell nanomaterial interaction. Very simple energy minimization problem. Okay, just a membrane interact with a fiber. I give that example. We already understand a lot. Okay, we understand this critical diameter. We understand why fibers can be toxic to, can lead to cancer, right? Like asbestos is known. It is known medically to cause problems, right? But we can give understanding why is that, why it happens. My second example has to do with the vesicle packaging of flexible nanofibers. So for the first time, we define what is a biosalt. Okay, what is because you know, every day we're facing lots of material, foreign material in our body. Okay, our body have to distinguish between self and foreign. Okay, so very important signal is a stiffness. Okay, when the cell sees something stiff, it wants to remove it. Okay, soft is okay. Right? What is soft? What is stiff? So here we introduce the stiffness as a way to buckling. It's simply governed by engineering principle. Okay, the engineering principle buckling within the packaging cell or packaging lysosome. That's a definition of the stiff, and we verified this using experiments. Okay, we did systematic experiments with various material. We show indeed the buckling criteria is what governs the toxicity of the system. The energy mapping, I think this is also the engineering and physical tools, computational tool. If we can map out the free energy interaction of the material and cell, we can develop new drugs. Okay, I'm just giving an example of antibiotics, but there's a lot of other examples I could have given, cancers and other things. Right? Once you understand the principles, then you can help speed up the pace of innovation. So with that, let me stop here. Thank you so much for your attention.
Thank you, Professor Gao. Maybe you have some questions?
Yeah, I have some question about the first topic. Has anyone, that may be a trivial question, but has anyone considered if the tube actually have some screening and there's a portion energy function, is it possible?
Portion.
So because when you enter, and if the tube is simultaneously spinning, then it will create a portion. So if you combine with the bending portions and yeah, so will it change the picture?
That's a very good question. I haven't considered. I do see some people in ETH develop these spinning robots, small robots.
But that would be, I don't know.
Right. So in principle, that could actually, okay.
Because I'm
Regarding
thinking
the
about
question
the
I-
driver, so if you add that complete carbon economy, it will make it very easy to penetrate. But how to make this speed? I want to say you have to have a very small robot.
Okay. Well, that's a very good question. I haven't considered that. I thought about that question. Thanks.
Any other questions?
Okay, you first. Okay, I have one question first of all, and you made an assumption of the mixed contact region between the one-dimensional materials and the cell level. So
Can you say it with louder?
yeah, I mean, why did you make the assumption of fixed contact region in your first work?
Oh, yeah, very, very good question. Yeah, that's a very good question, actually. Yeah, here, right? So the contact area, I assume is a fixed contact region because of time scale. Okay. The contact area changed by bringing receptors from far away by the diffusion process.
Yes.
You have to bring more receptors, that contact area increases. That's a slow process. That's an order of, so the endocytosis cell takes about 20 minutes to an hour. Right? It's a slow process. But this biophysical process of rotation is a fraction of a milliseconds. There's experimental evidence. 2 time scales are very different. Okay. So here we're talking about, we're freezing out the slow time scale to simplify the problem. Because that problem is very slow, right? Within that time scale, you have plenty of time to adjust to equilibrium. Right. And we use, so of course it's an assumption. We developed this and we checked with experiments. Right? And so it was supported by experimental observation of rotation very fast. Okay. So the rotation on fiber. It's almost dynamic. People have done experiment, for example, using biosuction experiments, right? You've got fiber poking out the cell membrane, you increase the pressure, internal pressure. Then that fiber will suddenly snapping. That time scale is a fraction of a milliseconds, very fast. Okay. But this contact area change, diffusion process is very slow.
So in this way, the nanomaterial is surface modified?
Yeah, well, the surface modification is included in our with the contact area change. The surface modification plays a very important role. Okay,
Yeah.
because that's you write on the free energy associated with interface, right? It's the binding energy times contact area. If the contact area is constant, they don't play a role in this. Okay. So we're minimizing energy, say which configuration the cell, what is the mode of the cell uptake question, right? But if you want to ask me another question, say how fast the cell, how cells uptake process, then the binding energy play a very important role. So depending on which question you answer, or you are interested.
I have a kind of general question.
Yeah.
So here you get into a kind of maybe objective size of the fiber, right?
Yeah.
AC. I'm wondering, this kind of nano technology. We are talking about the scaling problem. For example, civil engineering. So, is this type of phenomenon also happening in the macro scales? For example, the larger scale can have the similar problem or not? Based on your analysis, sounds like it's more like a kind of
Right.
mathematical and
They used to compare a cell on the property of the cell. The membrane tension, the bending rigidity. These are lipids. They have to do with basically the biological material properties. So this gives us nanoscale.
Yeah.
But if you can select these properties in some other ways, you can make a macroscopic. The mathematics is applied to, it doesn't have a, say it has to be nanoscale. Just happen this problem is landscape is nano.
Yeah, because this is a very beautiful story, yeah, I can tell. But I think if we are talking about the larger scale, maybe we can have some other beautiful story for the civil engineering problem too.
Right.
Also here, you're talking about the fiber.
Yeah.
So did you ever also consider, for example, this type of graphene, planet, or this type of other geometry? Yeah.
Right, maybe the graphene, like two-dimensional material. Right? Yes, I have a project on 2D material. We're working very intensely on 2D material right now. I just didn't have time to talk about it. I can send you some paper if you're interested. Yeah.
Very interesting work. I think it was a very elegant combination of experimental work and also theory. So I was curious, one of the examples of a fiber on the surface of a cell would be the cilium of a cell. Each cell has a little bit of tail, about 1 to 10 microns long, probably about 100 nanometer wide. I think application of this model to understand, the cilia would be very interesting.
Yeah. That's a very good question. Yeah, I haven't thought enough about the cilia.
I think it's there. I wouldn't be surprised if it's applicable. It's really, you can define the value for the biosoft for sure.
That's a very good question. Thank you.
In that case,
Thank
yeah.
you. Thank you.
Yeah, thank you for your presentation. That is a very interesting theory, but I believe there might be multiple nanomaterials, the ones penetrated to the membrane at the same time. That or
Multiple nanomaterial.
yes, and for example, from the experimental image, if there's a membrane, I believe there could be like multiple classes.
Yes, that's right. Right.
Yeah.
For example, here we have two actually. There's
Yeah.
a bitube. There's the gold nano. Actually, the two of them together get into the cell. Yeah.
So in that case, there's that one single.
Yes. Basically, our theory says the diameter is key, right? If diameter is small enough, the cell will take it off. If the diameter is too big, then it will not go in. Okay, and we see in each case we see this, the enamel that goes into cell are thin fibers, 1 or 2, 2 or 3. But if you have a large bundle, they don't get in. Right? So there's a critical sizing factor. Right? So cells like to see nano. Basically, in nature, I think it makes sense from the evolution point of view. Cells have been trained or have been evolved to be sensitive to food, right? The food molecules. They want to grab everything, or bacteria. They want to grab everything nanoscale. Okay? If the scale is large enough, it doesn't pay attention. Right? So it makes sense to me. There's a nanoscale size. Okay? If there's a fiber, if the tip is small enough, cell will grab it.
So, is it possible that very small nanoparticle will be one with the same membrane?
You're talking about nanoparticle fiber.
Yeah.
Particle. You mean the
Two
spirit?
fiber enter very close to each other or something like that.
Right.
And
If you have a bundle of fibers.
Not one
well, they're not bundled, but they're very close to each other, so you get another energy minimization.
Yeah.
Configured.
I have not. Well, with the bundles, they're bundled together. You can treat it as a large. But you're saying they're close to each other.
Yeah, but not attaching each other, but just
Right.
2 or 3 very close to each other.
Very good question. No, I have not looked at the problem even. Yeah. In experiment, we don't see that often. It's too close by. Yeah. Yeah. If we see that experiment, we would go to model that. We haven't seen that. The experiment we either see a single fiber or a few of them together get in the cell, or we see bundles just lie on the cell surface. We don't see like they're close by to each other. It could happen in principle.
Or if they have, or if you solve the minimization problem, you may get 2 different pair of angles or whatever.
It's a very fascinating mathematical problem, but we just haven't gone in that direction.
Maybe the last question. Any? Okay, if you don't have, let us thank Professor Gao again. So the tradition of the department is to give a certificate to recognize your lecture. Thank you very much.
Thank you very much.
Thank you for coming.
Nicole?